In this lecture, we're going to rotate the player with a technique called linear interpolation. Sounds like a complicated concept. Let me break down the mysteries behind this feature. First things first, we should understand the idea of interpolation. Interpolation describes the process of calculating a value between two other values. For example, let's say we need to grab a value between 0 and 100. We may want to grab a value that's 40% of the way to 100. If we were to do the calculation, the result would be 40. Calculating the value is known as interpolation. Unity provides a formula for performing this calculation called linear interpolation. There are different formulas for performing interpolation. However, those have different use cases. For our game, linear interpolation is more than suitable. Inside Visual Studio Code, open the movement file. Let's focus our attention on the rotate method. At the bottom of the method, update the transform.rotation property to quaternion.lerp method. Previously, we were reading from this property. It's also acceptable to update the value. This is how we can perform rotation on a game object. By directly modifying the rotation value, the game object will reflect these changes. As for the lerp method, it's short for linear interpolation. There are three values required by this method. First, we must pass in the starting and end values. In our case, these values would be the start rotation and end rotation variables, respectively. The last parameter is a value between 0 and 1. 0 represents the starting value. 1 represents the end value. If we pass in a number between 0 and 1, Unity will figure out the respective value between the first two parameters. The question is, why are we using linear interpolation? Keep in mind, we're trying to smoothly rotate the game object. This situation requires us to smoothly calculate the rotation values on each frame. We can't jump immediately to the end position. Linear interpolation will help us perform that calculation. Rotating a player should be based on time. Otherwise, we'll face an issue with frame rate dependence. Let's pass in the time.deltaTime variable. Luckily, this variable contains a value between 0 and 1. It'll be suitable as a value for helping us calculate the new rotation. Before testing our code, we should multiply this value by the agent.angularSpeed variable. If you can recall, the angular speed setting can be found on the agent component. This setting determines the speed of an agent's rotation. It won't be applied to our calculation. We should include it to allow designers to configure the rotation speed. After making those changes, let's try testing our code. Head back to Unity. Next, play the game. As you can see, the blue box is moving around. This game object was added to help us identify the forward position of the player. It should be facing the direction you're moving in. At the same time, it should not be moving when we're not moving. Perfect. We've successfully rotated the player by updating the transform component's rotation values. Linear interpolation has helped us by creating a smooth rotation. We're finished. The goal of this section was to move the player. If you made it this far, pat yourself on the back. In the next set of lectures, let's wrap up this section with some final thoughts.